Welding is a much more permanent connection than bolting or riveting. It's the connection of two metal objects through melting some weld metal and allowing it to fuse with a parent material at much higher temperatures than soldering or brazing. We're going to talk about using a lot of material from a textbook by Norton, Chapter 16, with reference to the Shigley text. Application to machine design. This is much different than welding for structural applications or for pressure vessels. Those are guided by codes and standards with which you must be familiar if you're going to do design. Alright, so what happens in arc welding? We have an electrode held close to the workpiece. It causes a 6,000 to 8,000 degree Fahrenheit arc to melt parent and weld metals together. And welds look like this. We've probably all seen a weld before. Here are some nice ones. You know, you're not supposed to look at the arc because it's too bright. Another nice weld there of one tube to another. Sometimes welds go bad. Here are some nasty examples. All right. So what are some of the main material implications of welding? Well, if you've done some hardening or cold rolling to improve strength, the high welding temperatures are going to basically undo that. Welding causes a lot of thermal expansion and contraction, so you often need complicated or at least sturdy jigs to hold your parts together so that they stay aligned after the heating and cooling of the welding process. It's easiest to weld low carbon steel. Aluminum is more difficult, takes usually specialized people. The thermal expansion and contraction can often lead to high residual stresses. In fact, the state of stress around a weld is very complicated. Here's a depiction of a simple fillet weld. We can see a triangle going from C to A to B. We're welding together two parts here, one along the line CB and one along the line AB. Here we can see the stress distribution in what are called the legs of this triangular fillet weld, which are the sides that are not the hypotenuse. So the stress state is very complicated. So we're going to do some simple stress analysis models which will allow us to design welds safely with some conservatism built in. To get good fusion, to get a good weld, you need to keep the molten metal very clean, free of oxygen. Okay, you don't want any oxidation or nitrogen bubbles to mess up the weld. So to keep that molten metal clean, typically a stream of inert gas is used to keep oxygen away. All right. So when you hear about gas welding, gas metal arc welding, that's what the gas does. You have to get good weld penetration. You need the molten weld metal to not just superficially, but to fairly deeply penetrate the parent material. And that gives you a final weld that is sometimes even stronger than the original material. The zone that's affected by the heat is called, well, the heat affected zone. And we can see a depiction here in figure 16.1 from Norton. And we can also see it in this microscope view of an actual weld. For high strength steel, the heat affected zone is weaker than the material that you welded together. For low strength steel, this heat affected zone is stronger and harder, and that can lead to cracking, especially with dynamic loading. So there's some terminology here related to welds which you can take a look at your own pace. So some processes. Stick welding, or shielded metal arc welding. So there's the stick of welding material is covered in a flux which covers the molten metal and keeps oxidation from happening. It's typically used outdoors. The gas welding, or gas metal arc welding, or MIG welding, that's the one where you direct the inert gas onto the weld to displace air. It can only be used in fairly calm wind conditions. TIG welding, or gas tungsten arc welding, uses a tungsten wire electrode, which has a separate filler material, and that also uses an inert gas stream. This is good for welding specialized materials like titanium, aluminum, and magnesium. Sometimes it's possible if to have a powdered flux which completely submerges the weld pool, and it also keeps the arc under this powder layer. So you don't need eye protection. You get a good appearing weld, and you keep oxidation from happening. In auto body assembly, it's often spot or seam welds. These are resistance welds where you pass a large current through a thin sheet of metal, and that the resistance of the metal causes the current to be turned into heat, and you get welding that way. There are many types of welds, and sometimes it requires that you machine a groove into your parts and fill it with the molten weld material. So, for example, the groove weld here. Okay, that one obviously requires a groove. On the next page, the butt weld, when you're just joining two pieces together flat like that, or the edge weld, the inside of the corner weld. Okay, we can see that there's a groove required there. So let's see, we can categorize the butt weld, the edge weld, and the outside of the corner weld to be groove welds. Fillet welds, such as the one shown over here, you're simply laying down a bead of weld material without having to modify the individual parts. So on the next page we'll see the T, the lap, and the outside of the corner. Okay, here we just see simply the weld material deposited in a fillet inside of the corner, a lap joint, and a T. The plug and the slot, that requires putting either holes or slots in one of the pieces and filling the hole with molten weld material. These tend to be a weaker type of weld. All right. Another sort of categorization of welds is complete joint penetration, where there's actually a gap between the two pieces, or partial joint penetration. Often in welds you see this little area, this little hump here, this convex surface. It's called reinforcement. It doesn't actually reinforce the strength, okay, so you don't count that when estimating the weld strength. When we're estimating weld strength, the big simplification we're going to make, the big assumption we're going to make is, and I'm looking at a fillet weld here with a leg width W, so these are the non-hypotenuse sides of this little right triangle here. So it's a W by W weld. The throat of the weld is this short dimension here. Okay, that throat T is 1 over root 2, 0.707 times the width. The assumption that we're going to make, and it's going to make our lives easier, is that when a weld fails, that the entire load on the weld is going to be a shear stress, and if failure occurs, it's going to occur along a shear plane with a dimension equal to that throat. So here's a little sort of depiction of a fillet weld to join two parts together. Okay, so I can see I got a right triangle there. Here I can see the throat dimension opening up. Okay, that's 0.707 times the sides of the triangle. There it is. So even if the weld is not a shear, but if there's basically a normal stress this way or a normal stress this way, we're going to do our design as if the weld failed along that throat dimension T. So why does that make things a little conservative? Well, talking about shear stress here. There's going to be a certain load on the weld. The shear area is going to be, as I said, 0.707 W times however long the weld is. I'll call the length L. So that's going to be F over throat times length. Okay, if I divide by the 0.707, I get 1.414 F over WL. Now in the Shigley book, they do some stress analysis of a weld. They consider a lap joint like this one. Here we have the little right triangle for the weld. They break it down into normal stress and shear stresses along the throat direction, and they calculate that the largest von Mises stress the largest von Mises stress, sigma prime max, ends up to be 2.16 F over WL. Now, if I think back to the distortion energy theory, if I set the sigma prime max, if I set that equal to the yield strength, I know my shear strength is 0.577 times that. So if this is equal to the yield strength, I'm going to have shear failure at 2.16 F over WL, which turns out to be 1.25 F over WL. We're going to use 1.414 F over WL for the shear stress. So the 1.414 is a little higher than the 1.25, so we have some conservatism in there. We're going to come back to that. Just keep in mind the weld throat is the shear plane, and we're going to treat everything as a shear stress. Now, how do we describe welds on drawings and whatnot? Well, all these different types of welds require a different preparation, and they have a different symbol. Okay, so the square edge joint here, we have a bevel, V, U, and J. We want penetration of the molten metal to all the portions of the joint area. If we use the U and the J, then the molten metal doesn't run out the bottom. We may need to use a backing plate with some of those other welds and then grind off or chip off the backing plate. All right. We also, if we can, would rather have a longer, continuous, smaller weld than a bunch of thick welds, because every weld, beginning and ending, causes a stress concentration. So before we get to the weld symbols, I'll just point out from this table. There's also a table 9.6 from Shigley, which is at the end of this document, which has the same information. There are basic minimum fillet weld sizes. Okay, so you're not supposed to have a weld bead less than 1/8 if you have a plate up to 1/4 inch. Between 1/4 and a 1/2 inch plate, you should have at least a 3/16 weld leg W, and so on. Now, the weld symbols can be kind of intimidating at first. There's an awful lot of information you can pack onto a weld symbol. Essentially, you're going to have an arrow pointing to where the weld is going to go, and you're going to indicate what kind of weld you're going to put on the same side as the arrow and what kind of weld you're going to put on the other side. And if there's a certain length of weld that occurs every so many inches or millimeters, you can put the length and the pitch on there. You can have various finishes. You can put the size on there. There's a little flag here if the weld is to be done in the field during field assembly. So I've included a number of symbols here. I'm just going to do a few examples here on page 6. So let's draw the weld that's indicated by the symbol. So we have an arrow here that's pointing to one of two sides of the 1/2 inch plate. Now, this side under the line is called the arrow side. So on the arrow side we need 3/8, and this symbol here indicates a fillet weld. So one of those triangular welds, 3/8 is about 3/4 of a half, so we'll have a fillet weld like that. Now the top of the line is called the other side. That's the actual technical term. So here the other side is around here, and now we need a 1/4 inch weld there, also a fillet weld. Okay, so there's the weld. Fillet, fillet. Alrighty. Here we have, once again on the arrow side, we're going to have a 1/4 inch fillet weld. So that'll be about half the thickness of that plate, so approximately something like that. And on the other side, which is the top of the line, I have a 1/8 inch. What's this symbol V here mean? Let's go back up to the example. So that V refers to, okay, a groove weld with a V. And that groove is going to have a certain root opening, which is the gap at the bottom of the plates, the little separation between the plates. And there's also going to be an included angle. So for the weld that we're trying to draw here, I've got a root opening of 1/8. Okay, so the root opening of 1/8. which means I need to have a 1/8 gap in here. Let's see, so about 1/4 of the width of the plate. Okay, so that's 1/8 of an inch. I got an included angle of 40 degrees. So I'm going to go down here and I'm going to draw some lines coming up from the bottom of my groove, which are going to give me that angle of 40 degrees. Okay, and then the weld is going to fill that zone. Okay, so there's my weld for that. Alrighty, finally right here I've got a U-groove weld. Having some scrolling issues here. I got a U-groove weld with a convex surface, and I got a 20-degree included angle. So I'm going to come up from the bottom. I'm going to have a 20-degree included angle. I'm going to have a U-groove. I'm going to fill that with weld material, kind of like that. Okay, and I'm going to have this convex reinforcement on top. A few examples of, here we have a weld pictured and we want to specify it. Okay, so I'm going to draw my arrow, and on the arrow side, which is underneath, I've got, what does that one look like? That one looks like the J-groove weld from the table on the previous page. So I put my J-groove symbol in there. It's got a convex contour, so I'll put that like that. In the final example, I've got a 1/2-inch plate. I can arbitrarily pick which I want to be the arrow side and which I want to be the other side. Here I've got 2 1/4-inch, well, actually I've got 2 1/4-inch welds. This one on the arrow side is a simple bevel, and I'm going to put the 1/4 there. On the other side, I've got a bevel groove weld. Okay, so I'm going to indicate that with this symbol. And if the included angle there is 45 degrees, then I'm going to put 45 degrees in there. And if it's also a 1/4-inch nominal weld, I'll put a size up there as well. Okay, so arrow side, other side. All right, so that's a little introduction to the qualitative aspects of welding, the weld symbols. And next we'll talk about some design principles, and then we'll talk about designing welds for strength.